Alright, this is a video solution for the computational thinking assignment, and this is important, especially if you miss this class, because this is kind of like a lecture at the same time. So you hear a little bit of explanation of computational thinking, and this will be addressed, these things will be addressed in the Chapter 0 test that is coming up. So as we look at this, in your homework, you were supposed to have read the following definition by Jeanette Wing about computational thinking, being the thought processes involved in formulating problems and their solutions. So the solutions are represented in a form that can effectively be carried out by an information processing agent. And then I added this little part here that the information processing agent could be a machine or a person. And this is a very Jeanette Wing here is a very good writer, and she's has done a lot of work on computational thinking, a lot of articles and so forth. And so she can write very in a sophisticated way, where a lot of times her words are big and the way she puts them together are very effective, but sometimes harder to understand. And so what I wanted to do was to kind of break this down a little bit. So if we go to number 2, because this is in discussing computational thinking, we're going to actually use computational thinking skills right now in this assignment. So it says use 2 words from here, from this definition, that you could use to explain or actually kind of represent this more complicated version. So it says fill in the blank. So computational thinking is a blank of blank. So what I was looking for, something like process of thought, or maybe process of thinking. So I was taking these 2 words and then kind of changing the order and then saying it's a process of thought. So you could actually take this entire definition and synthesize it down to very generally that this is that computational is really a process of thought. It's a way of thinking. And so as we go on here and we look down further now, it says that let's see if I can do this. Then rewrite the above definition using words, terms, and phrases that are more easily understood and more relatable to yourself. So that I'm not going to give you any answers on, but this students that gave their ideas in class did very well. And so if you were able to rewrite this, not using the exact same words, but in words that made more sense to you even, then that would be helpful. And so the question here is, why do you think the following statement should not be whoops, I want to do this. Let's change something here. Okay, I made a little adjustment here. And so why do you think the following statement should be considered to be true? Computational thinking is not just for computer scientists or computer programmers. And so the thing is that we have to solve different types of problems in school and in our everyday lives. So every single one of us are going to have situations that we're going to have to problem solve. We have to figure out, well, what is the solution to what I'm dealing with here? And if you think computationally, that's going to help you be more effective in coming up with that solution. And we'll deal with this in school, and in high school, college, on our job, in our relationships with our families, etc. So computational thinking is not just referring to or just necessary for those that are working on computers and writing computer programs. It's for everyday life. And so as we go here, here's an example. This isn't a computer, but computational thinking could be used. And so you have a 500-piece puzzle. What kind of steps would you give that would that somebody could follow, and they could help them put the puzzle together more easily? And so I wrote down 3 steps, which isn't the best, but step one, sort the pieces by corners, edges, and colors, place down the corners, and then add edge pieces to form a frame, and then add pieces inside the frame based on color and shape and things like that. And so these are just 3 basic steps that can be done as far as putting together that puzzle. And so we go on, and you're going to see how this is going to relate later on. So it says use the internet to help fill in the blanks. And so the idea was for you to do some research on these, and of course these words in here, decomposition, computational thinking, give you clues as to what kind of words to do your search. So hopefully you did that, and you found out that decomposition is breaking up a problem into smaller parts. Now if you have something that means the same thing, you don't have to have exactly what I have. But if the idea is that you break something down into smaller parts, and so that's just like decomposition, like something decomposes. It's being broken down, and that's what we're doing with this. So the question is, describe how you think decomposition relates to putting a 500-piece puzzle together. And so by grouping the different types of pieces into smaller groups, that's breaking up the problem into smaller parts. So you're dealing with just the edge pieces, dealing with just the corner pieces, and then you're dealing with, maybe you separate by color, and so you have the ones with a certain color is a smaller piece of the whole thing. So this is a very important thing, is to be able to break something down into smaller parts. The important thing about decomposition as a computational thinking skill is that if you think about word problems that you have in math that look huge, you go, I don't understand how I'm going to be able to pull this off. Or maybe you have projects that you have to do that encompasses a lot of things, and you're going, I don't know how I'm going to get this taken care of. If you learn how to break a problem down into smaller parts and then work with each part, each part's going to be simpler to work with. And then eventually you finish the entire word problem or project. And so decomposition is a very important part, and I find myself doing this type of thing often. It's breaking up a problem into smaller parts. The second thing is pattern recognition, which I think most people understand what that means. And so it's seeing things or themes that are being repeated oftentimes. And so you describe how you think patterns relates to putting a 500-piece puzzle together. Examples: when you look at the picture on the puzzle box, you are looking for patterns. You're looking to see all the edge pieces, so that there's a pattern. You are looking for all the ones that have that straight edge. You're looking at the ones that maybe have 2 straight edges to form a frame. You look to see patterns of colors and different shapes. And so you're looking at patterns, trying to recognize patterns. Now that can help you as far as being able to solve a problem, in this case putting together a puzzle. Then abstraction, which is what I'm going to spend a little bit more time on, is because it's a little bit more complicated, but it's hiding, abstraction or pattern generalization is hiding details from a solution. It's representing a group of details in the form of a shortcut. So just to give you an idea, when you use formulas in math or functions in math, sometimes all you have to do is just plug in the certain numbers, and you do the calculations, and voila, you've got what you need. And you're going, well, if you didn't have that formula, you would have to do it the long way all the time. And so a formula is something that takes a group of details or steps and reduces it into a shorter form. So all you have to do is plug in the numbers, do what you got to do, and bam, you got it. And what that does is hides the details. In other words, it filters out the details of working that whole problem and figuring it all out, where the shortcut, the formula or the function, removes those details. Here's another way to write this down. Abstraction is representing something complex with something simpler. Okay, so for instance, if you were to, as an electrician, you were going to hook up a switch, and so so we've just flicked the switch on and off to turn the lights on and off, but there's a lot that goes into all that. What really happens? There's a certain cords or wires are connected to certain things, and you have an open or closed circuit, and you have all kinds of things, and it can be kind of complicated. We don't care about that. The details of what's happening when we flick the switch on is hidden to us. We don't care. All we care is that when we flip the switch on, it either turns it on, turns the light on, or turns it off. And so what's happening is we're representing the switch, the light switch represents all the processes that go on to make it work, to make electricity flow and everything. We just represent all that with just a flick of the switch, the shortcut. So when did we represent something with something simpler in this assignment? And so if you think about that, up here in this question, we took something that's a little bit more complex, and we narrowed it down basically to this one small statement. So this becomes our abstraction. It hides all the other details that are in here, and just brings it down to this. So we don't care, maybe this might be adequate for certain things where we don't need all the other details in here. And so we represent this whole paragraph or huge sentence with a smaller sentence. Okay, this is right here is the abstraction. All right, so let's go down here, and okay, we're going to skip this part. This part, if you were absent, you didn't have to do the binary code activity, so you don't have to worry about this. So let's just go on to here. Abstraction examples. A graph can be an abstraction. A graph will here's an abstraction because it's leaving out different details in here. Like you don't see on these bars the exact number of people that said this was the nicest fruit, although you could look over the numbers over here. But if you're just looking at this, this takes out some of the details, and so you could look at here immediately and see that blueberry is is the choice that people picked for the nicest fruit. Here, another example is a map. A map is an abstraction. So here's a map, but this map, maybe you might use this map to show a little kid, where Phoenix is in relationship to the rest of the United States. Well, this is an abstraction because it's filtering out other details. It's filtering out all the other cities in the country. It's filtering out roadways like freeways, and it's filtering out rivers and different things like that. So there's a lot left out, but maybe this map is the solution to the problem. Show a kid where Phoenix is in relationship to the rest of the United States. And so this is an abstraction. Another abstraction might be a template, where all you have to do, where somebody else has done the work, the main part of the work where they've set up the things, and then you just type in and fill in the details that you need for your situation. Like we said before, formulas, functions are different abstractions. A model or a simulation, Mr. Hestenes teaches aviation ground school. They plug in these simulators into the computer, and then they fly. It's like they're flying, only they're not really out in the air flying, but they're able to do this because of an abstraction. And so it filters out everything else, and they can actually do the important part, like steering and different things like that. All right, so let's go on. The last thing is algorithm. Algorithm is simply a list of properly ordered steps that allow a person or a computer to complete a task. It can't just be any list. It's got to be a list that has order to it. So if you were giving somebody directions to your house, the steps better be in order, or else they're not going to get to your house. That would be an example of an algorithm. Anything that shows directions on how to do something, you basically need to follow in order to accomplish it. That is an algorithm. Did you write an algorithm somewhere in this assignment? Well, we kind of did in number 5. Now make it a list of steps that someone could follow that would help them put the puzzle together. Whatever you wrote in here, some people actually did step 1, step 2, step 3. That's an algorithm. And so let's see here. And then write an algorithm for getting ready to school. So hopefully you wrote down a list of steps that you would follow in order that would help you prepare for getting ready to go to school. All right, that's it. And remember, this computational thinking will be on the test coming up. And that's it.